Let's now understand in some detail what happens on each of the nodes, previously known as the minions in a Kubernetes cluster. Let's go back to our favorite diagram. Remember that a Kubernetes cluster consists of instances. These could be bare metal machines, these could be virtual machines running in a local data center, or cloud virtual machine instances running on a provider like the Google Cloud Platform, AWS, or Azure. We have already seen how Kubernetes will designate one or more of these instances as the masters. The master or the control plane will then consist of different processes. Let's now turn our attention to what happens on each of the individual nodes or the minions. Those are the remaining instances which do not run the control plane. Each of these instances again could be a VM or a physical machine depending on the nature of the cluster. But uniformly, these nodes or minions as they used to be called are going to run three important pieces of software. The first of these is going to be a kubelet, the second is going to be the kube proxy or the network proxy, and the third is going to be the container engine, usually Docker. Let's double click on each of these. As its name would suggest, the kubelet is the Kubernetes agent running on this node. Once we install the right kubelet software on any Linux machine, that kubelet will start to run. It will seek out a Kubernetes cluster and it is going to try and listen for instructions coming from that master. So the kubelet is going to listen in on commands which have been sent from the control plane. So let's say, for instance, that a new request has come in to create a certain pod. That request was sent by the user using a YAML manifest file to the Kubernetes cluster. It was picked up by the API server, parsed, and then handed over to the scheduler, all of which runs on the control plane. The scheduler then made a decision. It decided that a pod needs to be fired up on some given node. The scheduler would then communicate with the kubelet agent running on that node and ask it to fire up a pod. Hopefully everything goes well, the pod comes up and that pod will then start to run a container within it, and the kubelet agent will report back success to the master. It is also possible that for any reason the kubelet is not able to fulfill the directions of the control plane. In this case, the kubelet is merely going to return a status of failure to the master, and it is then up to the master, the appropriate element in the control plane, to decide what to do next. By the way, you should know that each node is going to expose the kubelet endpoint on port 10,255. So you can always go ahead and inspect the kubelet agent on this port of each node. Let's move on now to another part of each of the nodes, and this is the container runtime. As we've already discussed a bunch of times, the basic unit of execution in Kubernetes is a pod. A pod is going to consist of one or more containers which are tightly coupled to each other. Now, of course, pods are going to run on top of nodes, worker nodes or minions, and therefore each of these nodes better have a container engine. The most common container engine, of course, is Docker. And so each of the nodes is going to run this Docker container engine, and the kubelet agent is going to work together with this container engine or container runtime to do all of the actual nitty-gritty, pulling the images which have been specified in the pod specification, starting and stopping containers, and exposing them on ports which have been specified in the manifest. Kubernetes clusters support two types of container runtimes, Docker and RKT. Docker is, of course, the dominant container runtime right now. You should also be aware that Docker is in the process of splitting out its container format into a separate component called containerd. This was donated by Docker to the Cloud Native Computing Foundation, CNCF, and over time containerd is likely to become the most popular and common container format. In any case, Docker and its likely heir apparent containerd are likely to remain the container engines of choice on Kubernetes. Kubernetes actually has a specific native way of interacting with Docker. This is called the container runtime interface, or CRI. The CRI is how the kubelet interacts with the container engine. And the third element that runs on the component is the kube proxy or the network proxy. This is something which is required for the IP addresses which are maintained by each pod. We'll have a lot more to say on the networking aspects of pods. For now, just suffice to say that each pod is going to have its own IP address, and that unique IP address is going to be ephemeral. So if a pod goes down, there has got to be a new pod created, and that new pod is going to have a different IP address. A lot of jumping through hoops is going to be required to get around this. More on that later. For now, again, just be aware that a network proxy or a kube proxy runs on each node, and this makes sure that each pod gets its own unique IP address. And these three components collectively constitute a node: a kubelet, a kube proxy, and the container runtime. Together, these are going to provide all of the support that is required for a pod, which is going to consist of a set of one or more tightly coupled containers. More on that in just a bit.